report to this computer. Okay. So today we're starting our first chapters. So this week, the goal for this week is to actually cover Thomson 1.1, which is on the standard model. We're also going to go through 1.2 through 1.4 very briefly because a lot of the equations they put in there are not derived for you. And then like if we try to use it, it just wouldn't make any sense. You wouldn't remember how to use it in the future anyway. But we'll do some qualitative, like, oh, what happened when the energy goes higher, like the high energy limit versus the low energy limit. So that's the type of thing we're going to look at in those sections and how each of these detectors work and why they work the way they do. So it's more of a qualitative chapter. I'm also going to try to cover the first sections of chapter 2, so we have more time for quantum mechanics next week. The first section is on natural units, and we're going to see why it makes sense for us to use natural units in high energy physics, particle physics, and we'll see how far we can get on special relativity because I think I'm slating us on a lot on the plate, and then see how far we get. So we may have to cover special relativity beginning next week anyway. Okay. So the first section is on the standard model, and the standard model covers, as I think I tried to hint this last week, is that it covers 3 out of the 4 fundamental forces that we know about, and that's electricity and magnetism, which is combined together. Those of you who took general physics from me will probably know why they are basically the same, because whether something is an electric field versus a magnetic field actually just depends on your frame of reference. It's not a real difference. And then there's also the strong force, which is covered by electrochromodynamics, and which is the stuff that binds nucleus and protons and neutrons together. And we're going to go through all these little particles in a little bit. But the last one that we're going to cover is going to be the weak force, which you'll also see is actually part of electromagnetic force. It will be combined with electricity and magnetism to make it the electroweak theory. It'll be actually be merged together, and gravity we're not going to deal with. Okay, we don't deal with gravity that in this class at all, because we don't really have a standard model that describes it and do calculations with it. And that's covered in general relativity, which is a completely different way to think about how interaction and how things don't actually interact with each other, but it's just a space-time changing on you, and that's a completely different type. And one of the idea is that the hope is that at some point in the future, right, all 4 of these forces can be combined together into a grand unified theory. That way we can cover everything under the same mechanism, so we're not we don't have this 2 different ways to make predictions and do calculations. Okay, so the first section here is going to be the standard model. Let's talk about what the standard model is. The standard model consists of these 17 particles. It's kind of nice that you don't have to memorize a lot of things, but there are these 17 things you have to get to know. Okay, so there are these things called quarks, which is in this purple stuff. Maybe pink, depending on your screen. Okay, the quarks are actually what makes up protons and neutrons in everyday life. It can make other stuff also, and we'll talk about that. And most of the quarks that we see in everyday life is the up quark and the down quark, and it's very creative naming there, because it's just one has a charge of 2/3. I should just use the pen instead so people can see me online. Let's do a red pen, right? Okay. And it has a spin of 1/2. Okay. And we'll talk about what spins are and how does that correlate to how things are formed together. Okay. The down quark has an electric charge of 1/3 the electric charge, 1/3 the electron charge. Okay. Remember the charge of an electron, Q of E, right, is about 1.6 times 10 to the negative 19 coulomb in this unit, and we'll get rid of this units pretty soon, because then we'll not have to deal with these conversion factors. Okay, it also has a spin of 1/2, and when you have a proton, right? A proton, I think there's probably a picture down below somewhere, is actually made up of two up quarks and one down quark, okay? Right? And remember that the charge of a proton, right? This is actually the absolute value, is the same as the charge of an electron, right? Also 1.6 times 10 to the negative 19 Coulomb, right? Since each of these up quarks has 2/3, right, of the electric charge, fundamental charge, right? The down quark has negative 1/3, right? If you add all this up, it adds up to exactly 1, right? So the proton has the same charge of a electron in magnitude, right? Because, right, there is made of two up quarks and one down quark, okay? Right. There are other generations of them, okay? Meaning there are like kind of like heavier version of them that we don't see every day. And usually these are produced in colliders and rare events, then we don't deal with them in the everyday life. But if you want to study them, you have to make them in these accelerators and stuff like that that we're gonna talk about hopefully tomorrow on Wednesday. Okay. So the second generation for quarks is charm and strange. And then the third generation is top and bottom. I'm not going to go through the facts of these things, but the general trend is that the higher generation you go, the more massive they are. They're just like bigger and bigger and bigger. Okay. I don't want to say bigger and bigger, heavier and heavier. Well, I don't want to say heavy anyway. Also, heavy is like also a gravitational link thing. More and more massive. Okay. All right. So that's the quark sector, and all of these, right, participate in the strong interaction. I'm going to see what these are, okay? The weak interaction and the electromagnetic. I'm going to put EM here, if I can figure out my pen, okay? All three forces, okay? All right, okay? And the next thing down here are what's known as the leptons, the little green guys down the bottom here, okay? The leptons. So the leptons are a little different from the quarks because they do not interact with the strong force, okay? So just the weak and well, actually I'm gonna write EM on top, electricity and magnetism on top, and then weak between the two, and we're gonna see why in a second. So hopefully everyone's heard of an electron. So electron is the lowest generation, lowest mass charge lepton. So this is a lepton that has a charge of -1 elementary charge, right? The charge on an electron is actually -1.6 times 10 to the negative 19 Coulomb. And this crazy units we use in general physics and intro physics to convert them to SI units. Okay, right. Before I go down here with the neutrinos, so there are also 3 generations of these leptons, right? So you have the electron. The next one up is called a muon, okay? And there's some history about why it's called a muon. And then the next one is called tau. Yeah. Once again, the same pattern happens where the electron is the lowest mass. So you can actually see the mass up here on the top left corner, 0.511 MeV per c square. So that's a unit of mass. So just think about it as just a number, okay? Bigger number, bigger mass. We're going to figure out what these units mean a little bit, okay? Okay, where the muon is 106, the tau is actually 1,777, right? So it's actually about 3,500 times more massive than the electron. So it's like a really, really chunky electron, okay? So all of these have electric charge, and therefore they also interact with electricity and magnetism, okay? So what happens is that the difference is that, well, the quark sector, but all of them have charges, right? Electric charges at least, okay? Where in the lepton sector, there are those called neutrino. Neutrino, the word neutrino hopefully dries up, oh, something that's neutral, right? Okay, that means they do not have an electric charge, okay? So there's no electric charge. The only thing they interact with is the weak force, okay? And neutrinos are almost massless. In fact, before 1980s, people thought they were massless. And then people started measuring the this phenomenon called neutrino oscillation. And in order for them to oscillate into each other, you actually have to have mass. But as of right now, we are not able to measure the mass of these neutrinos so far because they are so small. Okay, just to give you guys a number, so the top left corner here for the electron neutrino, right, is a less than 2.2 electron volts per c squared. Okay, compare that to the mass of an electron, which is 500,000 electron volts. So the mass of a neutrino is about 250,000 times less than the mass of an electron. An electron's already very light, right? Okay, so this is why it's very difficult to measure these things, because they basically go at the speed of light whenever you put a little bit of energy into them, and it's really difficult for us to determine what their mass is. Okay, right? So the stuff on the left-hand side here, all this stuff over here, whoa, why does it give me a white screen? Okay, never mind. All of these things are also called fermions, and we're gonna talk about what fermions are, okay, when we actually get to derive them, okay? But what's interesting is that all of the matter is always made up of these things on the left-hand side, okay? The stuff on the right-hand side, or actually what's known as gauge boson, I'll just call them bosons, okay? We don't need to add the gauge into them, okay? And we're gonna see what the difference between fermions and bosons is in a second down here, right? But just to go back to the fermions, so notice that all of them have a spin of 1/2, okay? And we're gonna see what spin means, okay? Fermions have spin of 1/2, okay? The gauge bosons, okay, all of them will have the spin of 1. Just to 1, okay? Okay? And we'll figure out what these spin things means, okay? Because it's actually going to be useful in our calculation when we're trying to make predictions out of them, okay? So there's the gluon, which is the strong boson. So, you know, that's the strongest one. So this guy is with the strong, okay? Photon, hopefully, are familiar to most of you because you can see. This is the electromagnetic boson, okay? And then the Z and the W, there's no names for them, okay? They're just letters, okay? These are the weak bosons, okay? Sorry for the messiness, okay? And when I was taking this class, basically that was it. There was these 16 things together, okay? Now that you're taking this class past 2012, we also, well, we knew the Higgs boson should be there, but we haven't confirmed it. But since July 4th, 2012, now we know there's also this Higgs boson, right? Which is actually a very special boson that has a spin of 0. It's the only fundamental particle that has no spin. And we're going to see why that's going to be important when we get to get a little deeper into some of the mathematics. Okay. All right. Any questions about this? I think there's a bunch of lists down here that's on the lecture note, but it's not. I think I talked about most of them already verbally also. Right? Okay. So by the end of this course, we're hoping that you're going to understand the interactions between all of these different fermions and bosons, and how that's also connected to the Higgs boson, which allows particles to gain mass. And this is something that's gonna, that's the goal of this class, to get to the Higgs boson so that we actually understand why the universe is the way it is right now, and why proton have mass, electron have mass, you know, and why they don't just smash into each other, annihilate, and then nothing exists. Okay. All right. Okay. So some of those vocabularies, right? So we have the standard model. So those 17 particles up top are the makeup of the standard model. And that standard model is really not a model, because when someone say model, you know, oh, you model this, you know, cloud as a sphere or something like that. You're making an approximation to things, right? In that sense, it is true that we're not this is not, the standard model does require what's known as parameters, meaning stuff that we measure in experiments in order to figure out how everything works. So it's not like I can just write down a piece of paper and then never do an experiment and be able to predict everything about the universe. Okay. So these are experimentally measured parameters. So there's 19 of them, and most of them are like the masses. Okay. If you include the neutrino, there's actually 26 also. Okay. And all of this governs the electricity and magnetism, the strong interactions, and then the weak interactions. Okay. So, and all of this is great based on this theory or called quantum field theory, which we will not do in this class because that requires so much more math than that we can. we'll just be here, all semester just to get to the beginning of the standard model. Okay. But the way we're going to try to formulate things is that we're going to take the stuff that theorists already learned from quantum field theory, and we're going to apply them in a way that it obeys special relativity and quantum mechanics. Okay, we're going to combine special relativity and quantum mechanics together. Okay, and remember, special relativity is kind of like the first part of modern physics, right? Where you do time dilation and length contraction and all that stuff. Okay, quantum mechanics is sort of like the end of modern physics, where you're doing, once again, the angular momentum of a hydrogen atom or quantum tunneling and all these unintuitive processes that happen in real life that quantum mechanics predicts and we're actually able to measure. Okay. As I mentioned, this is still an incomplete theory because it does not have gravity in it. Okay, so gravity is important, right? Because that's the only reason where I'm standing here and not floating in space. Okay, but just to think about the scale of the standard model. Okay, so the standard model has prediction that tells you about the entire universe. It tells you how galaxies form. It tells you how stars form, how planets form, right? And how human beings behave. Well, not behave. How we work, basically. All the electricity, magnetism inside us, right? And it goes all the way down to the atomic level, subatomic level, meaning inside an atom, right? How does, basically the hydrogen model, hydrogen atom model is an electron and a proton, and the electron is kind of a little fuzzy cloud around it, right? That's already subatomic because you're looking inside an atom and how that works, right? Okay. But also nucleons meaning protons and neutrons. I'm going to write those out if I can with the 10 neutrons. Okay. There are other, nucleons also, but not even that, right? Inside the proton, right? As I mentioned, inside the proton, there are up quarks and down quarks, and there are gluons. And we're going to see why these are a little squiggly line like this, linking them together. Okay. There's actually a lot of them inside a proton. Okay. Okay. And that's the range that the standard model can actually make predictions on, and which is, already a fantastic thing. And if we get gravity into it, then we're done. It's like we finish our homework. Okay. As I mentioned, there are 12 fermions. So remember up here, right? All the stuff on the left, right? All the quarks, all the leptons, they're considered fermion, and they're special because they all have spin 1/2. Okay. And here's the list in the textbook of all the fermions. We're not going to go through all of them, so you should read that yourself. But this picture is kind of neat, where it's showing you kind of like to scale how big, how massive, right? The top quark is. So this T here stands for the top quark, okay? And then the tau is down here. This is a lepton, okay? This is the tau lepton, okay? The different scales and how massive or less massive things are to each other. You notice that the stuff on the left here, right? All the neutrinos are basically massless, right? Okay. And we have the first generation, right, which has low mass. As you increase in generation, you get more and more massive. Okay. Hopefully that pattern makes sense. Okay. Okay. Right. The neutrinos are kind of special because we haven't measured their mass, so we're not sure how to actually arrange them. Okay. This is actually a fundamental problem in neutrino physics that we're still doing experiments to try to learn, okay? And as I mentioned, there are the 6 bosons. So the bosons are, the photons, the W and the Z bosons, and then the gluons, which has these like kind of cool billiard ball type of multicolor thing. And we'll see why it's actually very important for them to have 2 colors, okay? Otherwise, none of this actually works, okay? Okay. But the goal of this lecture is to figure out how can we at least qualitatively qualitatively figure out what their interaction is, what is allowed, what's not allowed, and then we're going to kind of get into the quantification of it, okay? So historically, these things called Feynman diagram, which is this diagram down here, okay, came after a lot of really rigorous work that's done by theorists and in quantum field theory in order for us to have these Feynman diagram to get a more physical sense of where, how strong, each of these interactions are. Strong as in not the strong force strong, like how often they happen, how probable it is, right? And which one is allowed, which one is not allowed. There's certain things that are not allowed, okay? And so this little diagram, basically is a way for, especially for experimentalists like myself, to understand what actually was happening when there are interactions between elementary particles, okay? Okay, so I'm going to erase this because I actually need to write on this, okay? So think about the vertical space, in this book at least, as kind of like the vertical axis as like space, basically like a distance between the 2 particles, okay? And then the horizontal is time. Okay, so think about this as like distance between things, okay? And this is a very qualitative thing. This is actually not how particles actually interact with each other. They don't come in exactly at this angle until hit each other, right? Okay. Okay. So the vertical as kind of like distance between things, and then horizontal is time. Some books do make things the other way, so that's just to mess with you guys. So we'll have some of the textbook will have time on the vertical and then distance on the horizontal. And that's to agree with like space-time diagrams and stuff like that. So maybe there's more theoretical textbook will do it the other way. So don't be surprised, okay? So just figure out which convention they're using and use that one for that particular book, okay? Okay. So these Fs here, right? They stand for the fermions, okay? Okay. And what's happening here is that a fermion is coming in, another fermion is coming in. So let's call this F1, F2 or something like that, right? And what's happening is that they're scattering off each other by exchanging some sort of boson, okay? So these are the fermions, so these are the bosons. Boson, okay? I'm gonna write these out so you guys have the fermion, okay? Okay. And this is how all interactions happen, which is sort of neat. There are bosons that couples to each other, and this is going to turn into a big mess when we get to QCD. But at least at the with the first type of interactions we're dealing with, which is going to be the quantum electrodynamic, meaning we're only going to deal with electricity and magnetism. These are going to be the type of interactions where you have fermions and they're going to exchange some sort of boson to scatter, to basically bounce off each other. The reason that happens because just imagine if you and your friend is walking on like a ice rink or something like that, and one of you throw a bowling ball at another, right? They're going to be bouncing off each other, right? Just to conserve the momentum. So that's why they scatter off each other like this. Okay. This little G here stands for the coupling constant, and for each type of interaction, meaning electricity, magnetism, the strong, the weak, they will have different coupling constants between them. And that basically scales how often and how probable these interactions are, okay? And so one thing that the book also warns you is that don't think of these as physical drawings. They're very conceptual, okay? It's just so that we're using these diagrams in order for us to conceptually figure out what factors goes into our calculation, okay? Right? What is the momentum coming in here for these fermions? What is the coupling between them? Okay, which boson is being exchanged between them, okay? In fact, these diagrams don't really have a direction in them, okay? You can see on top of this diagram, this gauge boson between them, right? This one, let's highlight that, right? Right, it's drawn vertically, right? Okay, so if you have a time axis that's going horizontal, if you draw a vertical line, does anyone know how fast you need to be going in order to do that? If you're able to traverse some space in no time, what is your velocity? People are shy because it doesn't make sense, but that's okay.
Light.
That's it. I'm sorry, go ahead.
The speed of light.
Even more than that. It's actually infinite. Right? Right? When delta x is non-zero and then delta t is zero, right? Because the horizontal axis is time, right? Is some number over infinity is always going to be infinity. Okay. So that makes no sense, right? Okay. In fact, what really happened is that let's say you have two electrons scattering off each other like this, down on the second diagram. The photon is emitted from maybe electron number one. I'm going to label them 1 and 2, so it's just so I can talk about them, right? Being emitted from electron number 1 and got captured by electron number 2, and therefore the two, are exchanging the bowling ball they're throwing between them, right? Okay. So you have some initial state with some electron coming in, right? 2 electrons coming in, 2 electrons coming out. Okay, you never really observe the photon between them, right? Because you don't. If you observe the photon between them, you actually interrupted that interaction. The bowling ball got captured between the two, right? What could have happened is that, well, maybe electron number 2 is the one that emitted the photon, right, and shot it out to electron number 1. So this could have been in a different order, right? But what happened is that in experiments or in real life, right, what we're going to happen is that you just see 2 electrons bouncing off each other. You never actually see the photon between them, right? Okay. When you never observe the photon, these are called virtual photons. In fact, in general, virtual particles are going to be part of inside these Feynman diagrams, so that you never actually observe them, but you know that they have been there in order for the two bowling for the electrons to bounce off each other, right? Okay. If you have 2 ice skaters skating parallel to each other, right? All of a sudden, the two just start veering off from each other. You know that they threw some bowling ball between them, right? I keep using this bowling ball analogy. I don't know if that works or something like that. Throw a rock between them, something like that, or a bag. Okay. 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 So that's the idea that these virtual particles are never observed, but we know they have to exist. Okay. Okay. So, and this makes things conceptually a little bit maybe misleading. I don't, but the way we draw the Feynman diagram is that we always make this photon vertical, okay? It doesn't mean it is traveling at infinite velocity. It's just that we can't tell which one did electron 1 emit the photon or did electron 2 emit the photon. We don't know what time order it is, okay? So we just take the average of the two. We just make them vertical, so we don't have to think about that, okay? In fact, okay, for the 3 fundamental forces that we're going to be dealing with, okay, there are going to be, these Feynman diagrams will be made up of these vertices, okay? These are different vertices. So you can see that this one up here, this one down here, is actually the top half of this interaction, okay? In fact, it's also the bottom half, right? But upside down, right? Okay. Okay. So that's the electromagnetic interaction vertices. So if you put 2 of these together, you have 2 electrons scattering off each other, right? Okay. So some of the rules that we use to make sure that people are clear what's being shown on these diagrams is that, right, you have your particle that's coming in, okay? an electron is a particle, not an antiparticle. And we're going to try to figure out how to deal with antiparticle in a second here. Okay. Okay. Since electrons only interacts electromagnetically and weakly, so we don't have to deal with the strong version of this. Okay. For the electromagnetic interaction, it's always gonna emit a photon. Okay. And then since it emitted a photon, right? If this electron was to keep going without emitting a photon, it would just go in a straight line. That's sort of how you want to think about it. Okay. But it did emit that photon. So in order to conserve momentum, it's kind of had this little, kink in this path. Okay. Okay. But, it still remains an electron that's just, shot off, a little bit of momentum or energy, however you want to do it. Okay. Okay. Let's not talk about this stuff yet, and we'll talk about that in a second. Okay. For the strong interaction, okay, similarly, all the quarks, okay, that's why these are labeled Qs instead of F, okay. Instead of shooting off a photon, it'll shoot off what's known as the gluon, okay. Remember, the gluon is the boson that couples to the strong force. Quarks is also charged, right? Down quark is negative 1/3 charge. Up quark is positive 2/3 charge. So quark can also be interacting with electromagnetic also, right? So I can, why is this doing that? Okay, so you can also draw maybe a up quark scattering off, having a vertex like this also. This is also possible, okay? Okay, because this has an electric charge. Anything that has an electric charge can emit a photon, okay? Okay, sorry for the bad writing. Okay. Try to be quick. Okay, the weak interaction actually has two types, okay? There's the one that involves the W, okay, it looks very similar. And there's the one that involves the Z boson, okay? The W boson is special is because any vertices that involves the W is always going to change the flavor of the particle. And what the hell is a flavor? Okay, so like strawberry, orange, banana, right? By flavor, we mean, is it an electron? Is it a neutrino? Is it an up quark and a down quark, right? These are different flavors. And technically, like if you're comparing like the muon to an electron, that's also kind of a flavor, but it's better to refer to them as different generation of the same flavor. Okay. Okay. So the reason for that is always changes flavor. So look at this little diagram here, right? So a W boson has an electric charge of either plus or minus 1 electric charge. Okay. So if it emitted that plus or minus 1 electric charge, in this case, it's going to be minus. Okay, let's just put a minus here. Okay, right? That electric charge cannot remain afterward, right? You already gave up your 1 charge, so you cannot have a charge afterward, right? That's why it comes out as a neutrino. In fact, this one is going to be an electric neutrino for the time being. And okay. Okay, that's how you change charged leptons into neutral leptons, all right? Electrons to neutrinos, okay? Same thing with muons, same thing with taus, right? They would each create their own generations of particles when they emit electrons. They can basically convert one particles to another, one flavor to another, okay? The Z boson does not do that, okay? This is one of the things that technically in the rule book, you could have done it, but we never observe it to happen, okay? Okay, right? So in this case, it's basically a neutrino emitting a Z boson and then going off as a neutrino also. It doesn't change to something else, okay? Okay. So I want to give you guys an example of the strong version of this, the quark version of this. So if I have an up quark, right, which has the charge of plus 2/3, right? I'm actually putting it at the wrong place. I'm just going to write it in the right place then. Plus 2/3. Okay. If it comes in, emits a W plus, right? What has to be the charge of the thing that comes out? Anyone? On Zoom or anywhere? You got 2/3, you lost a full charge. What has to be the remaining charge here? -1/3, yeah. And what type of quark would have a -1/3? A down quark. And also the strange quark and also the bottom quark, okay? And these all are possible, okay? But mostly it's going to change into a down quark, okay? And we're going to see this in when we get to the QCD part. Much later, okay? All right, so just to finish up with these interactions, okay? When you combine these two things together, you can imagine combining them in different ways. So this is, this diagram here is known as the T channel, meaning it's the one we've been looking at a lot, where the boson exchange between them, right, is just kind of a straight line between them, okay? But what could happen is that you can also, swap the outgoing particles, right? If we call this electron 1, electron 2, right? This is still electron 1, this is electron 2, right? But you can have a case where 1 and 2 comes in, but then 1 goes out this way, and then 2 goes out that way. That's actually technically a different diagram, okay? Okay, and for some reason, the book didn't put this here, but there's also what's known as the S channel, where basically what's happening is that you have a positron, a positively charged electron, flying in here, and then annihilating with a electron, creating a photon, and then emitting a positron and an electron afterward. Okay, and this brings up sort of an interesting case. You notice that even though the red arrow here, oops, it's not on the board yet for some reason. Okay, the positron here, right? I say it's coming into the vertex, right? I'm drawing the arrow going out. Okay, anytime there's going to be an antiparticle, okay, it's always drawn with the arrow going out, so that way you can just have, so these arrows are actually tracking like particleness moving around. That makes sense. And we're gonna see why it is completely necessary for us to have antiparticles in our universe, and that's the only way these will work. Okay. I guess I won't have time to do the little exercise today. So Alex, I don't think we're gonna be able to do the little exercise today, but that's fine. We'll do that the first thing on Wednesday. Okay. So each of these diagrams, okay, Feynman diagrams are a passable path for these scattering to happen, right? So if you have electrons, 2 electrons, okay, both of these are possible ways for the scattering to happen, okay? But what happens is that when you measure them outside, you don't know which one is which, right? You don't know if, especially since if they're identical particles, right? One electron looks exactly like another electron. So when these comes out, oh, well, in the experiment, you don't know whether or not it's the T channel that the scattering happened off of or the U channel, okay? In quantum mechanics, when you don't know which one is which, what do? You guys remember? You add them, add what between them? Does everyone remember those keywords? Anyone on Zoom? When 2 processes happens, right? Add what? Sorry, can you speak loud? Sorry, I still couldn't hear you. You superimpose what between them? Do you add like their funkiness? What is it called? There's what? They are imaginary numbers. Anyone on Zoom remember? What do you add between them? Okay, so since anyone on Zoom, actually, it might be interesting to hear. Zoomland, are we still up there? Sorry. Okay, so I think I wrote this somewhere down here, but what you add is actually their amplitude, okay? And it's actually the amplitude square that gives you the probability of that process happening. So let's say I have this T channel process, right? Right. So this has some numbers associated with it. So okay, so this has some amplitude associated with it. Amplitude. Okay. And then the U channel has some amplitude associated with it. okay? Since you cannot tell it's a T channel or the U channel, okay, what you do is you basically square both of these together. So they could, I think you guys were trying to say this, they will could constructively or destructively interfere with each other depending on the phase between them. Okay. All right. Okay. So that's
Quick
how.
question.
Yes.
Quick question. What is the significance of T channel versus U channel versus S channel?
They are physically different, right? So one of them has an electron coming in, the same electron coming out, right? The electron one goes in, electron one goes out, go up north, I guess, go upward, right? And then the second one, you have the second electron going downward. And but if electron two was to cross path with electron one, and this is actually a different particle, right, that came out on the top, right? It is a completely different as if you cross path. And then imagine like, you have like a twin brother or something like that. You can play this trick, right? Where you cannot tell the difference between the two. So, but if this case, if down here is like a muon or something, and you can tell the difference between them, then you would not have this quantum interference process. Okay.
So in T channel, do they always have it where the particle on the top stays on the top? The
Yeah.
U channel,
Yeah.
they swap. Then
Yep.
the S channel does some sort of other configuration.
Annihilation, which it can't be the same particles because they won't annihilate. Yeah.
Gotcha. Okay,
Yeah.
thanks.
Do you mind, Professor Tu? I know we're almost out of time, but do you mind if I interject a couple things?
Yeah.
Just quick. I just want to say, because I know at Sonoma State in our modern physics classes, I don't even know if they use the terminology of amplitudes. Like,
Okay.
I think we don't really learn about that till real quantum mechanics. So, and I thought that might be the true at other institutions as well. So just, if you aren't familiar with that terminology, one way you can think about this is, so in quantum mechanics, as Professor Tu was saying, right, all we see is that 2 electrons have come in and 2 electrons have come out. And we have no idea what happened in the middle because we don't directly observe that. In quantum mechanics, these things that we haven't observed, it's sort of everything that possibly could have happened. In quantum mechanics, it says all of those things did happen. But some of those things are more likely to have happened than others. And that'll depend on things like how strong the coupling is, whether it's a strong force interaction or a weak force interaction, right? That'll tell you how sort of likely that intermediate process was. And so the reason we draw these Feynman diagrams is it's a way of organizing all of the possible things that could have happened in between these 2 electrons scattering. And then we add up sort of the likelihood of each of them, and then take the magnitude squared as Professor Tu has showing on the screen there. And that tells you something about the probability for that process to occur. So I don't know if that's helpful to anyone, but in case you hadn't heard that amplitude terminology yet.
Yeah, we'll talk about that after. Sorry, the students local couldn't hear you at all. That's why.
Oh, sorry.
Yeah. Yeah, we'll discuss that. And okay, so what I want to do is just, let's see. Yeah, I think we can just start off at this point here on Wednesday. And if there's any student who's still struggling with Canvas, registration, all that stuff, I'll stay a little bit after. Okay. So let's just wrap up here. Okay.